Welcome to this presentation on homotopy d-manifold. It's first of all a memo to myself. I was thinking this spring about these objects, classes of graphs, and it's also a little bit of a technology demonstration. We all had to be more creative this last year using lots of technology, and there was a lot of opportunity to try out new things, and I have made use of different techniques, like use of different cameras, several cameras, the use of objects, the use of video, and the use of virtual objects which I can present here. I can, for example, present a graph, a network graph like this, so I can also hold it in my hand. So virtual or real. And so the topic is graph theory, everything is finite. And I was thinking about the crazy question, what is space? So this is a stupid question because we cannot really answer it. We have no chance to answer it because the only thing we can do is measure distances, we can measure properties, we are finite creatures, we can do finitely many measurements, we can take a scanner and measure measure distances to an object and represent it in a point cloud. And these objects which we then have in the computer, these are finite objects. The true nature of space will always be hidden to us. But it's interesting, what a scientist does is look at models of space, and we have looked at Euclidean space. That's a good model. It is very successful. It has rotational symmetry. And we look also at discrete models. These are discrete models of space. This is a discrete sphere, and we can understand and work with this and see what we can do. Now, there is a big problem when we look at discrete spaces, when we look at finite representations of space. And one of them is that even though they might be very fine triangulations, the symmetry is broken. And if you look at the experiments in physics, there is no indication at all that space is discrete. We have really rotational symmetry. We have gauge groups which are continuous rotation groups, Lorentz groups, and diffeomorphism groups in general relativity. So there are lots of different symmetries, but they are all appear to be a continuum. Now, I was looking at the notion of a manifold which actually gets rid of this restriction. So we have, in some sense, and I will tell you at the very end, that was part one, why I'm doing this. Part two, I want to talk about the notion of d-manifold. It's a notion which emerged in the 1990s. Ivachenko, who was at MIT, and there is former this is digital topology, and this is discrete Morse's theory. So what you especially have to answer the question is, what is a sphere? And because what you want to have for a manifold is you want to have locally, that space locally looks like Euclidean space. And so the sphere in a d-dimensional space should be a d-1 dimensional sphere. So here is the setup. So we start with inductively, we have 0. This is the empty graph. We have 1, which is the one-point graph, just 1 point. And this is what we call a -1 sphere, and also a -1 manifold. Now, it was a question of while to characterize spheres combinatorially. You cannot do that with just the numbers, like the number of vertices, edges, etc. And there are different manifolds which have the same f vector, the same combinatorial data, but one of them is a sphere and one of them is not a sphere. You have to use some other notion, and the notion which you can use, one of the notions which you can use is homotopy. So this is a homotopic to 1, and then you define inductively what is homotopic. So when you have a network given, you'd say it is contractible if you can take away a vertex. So in this case, this vertex here, V, you can take that away because the unit sphere which you have here is contractible. And so inductively you define what contractible is. Well, that's the definition, inductive definition of contractibility, which has been obtained already in some sense by Whitehead I always mix up, there are two whiteheads, so that one of them is the English kind, one of them will actually lived in Arlington also for some time, Winchester and Arlington, but it's the English. They both worked on homotopy. We use this simple definition that something is contractible. We use the notion of contractibility. The notion of contractibility means that you can take a vertex away such that the unisphere is contractible, and when you take and the graph without that vertex is also contractible. So that's contractibility is something completely different than homotopic to one. So contractibility, so sometimes this is actually meaning homotopic to one, but I want to kind of make sure that there is no confusion. Homotopic to one means you also can extend this, so this is a completely different thing than this. So this is easy, very easy to check. You just look at all the vertices, see whether you can remove them, and if you can, then you remove it and you see whether you can get to a point. This is hard. Actually, this is not computable. There's no Turing machine which takes a graph as an input and decides whether it's homotopic to one or not. So what we have is, we have this notion of contractibility, and what we want, then we want that for a manifold, d-manifold, we want every unit sphere, we want to be contractible. We want to be a sphere. So these are examples of two-dimensional graphs which are spheres. But what is the property which makes a sphere? And the beautiful thing is that allows me to actually play a little bit, become a kid again, and play with toys. It means that a sphere means that if you take a point away, it should become contractible. So I have a couple of spheres here. I always wanted to do that. So I have here a couple of spheres around here, and let's just see. Let's just try this out here. So the big one, let's take the big one here. Close your ears. Let's try a couple of more here. A sphere is a d-manifold which is contractible if you have taken one thing away. So it's also easy to prove things in this framework. For example, I once in the math table kind of gave this proof, which is actually here. It's a two-line proof that spheres have Euler characteristic 2 in even dimensions, and in odd dimensions it have Euler characteristic 0. So you can prove that just by induction. So in this case, you prove this by taking away this thing, and you use the property of the valuation property of the Euler characteristic. So this has Euler characteristic 1, this is Euler characteristic 1, and the intersection is Euler characteristic 0. So the total sum has Euler characteristic 2. So what happens is with spheres is they are just a union of two balls. And one can also say that these are the manifolds which have Lusternik-Schnirelmann category 2. The sphere is an object. When you take away one point, it becomes contractible. And that's what we have just demonstrated, right? So this is a little bit a demonstration how powerful this is. This is quite old. It's 6 years old, and it's too easy to be published. But it's the analog of Sard's theorem in the continuum. Sard's theorem in the continuum says if you have a manifold and you have a smooth function on it, then the level surfaces are submanifolds, d-1 manifolds for almost all function values. Let me just demonstrate it. I can demonstrate you here how wonderful these definitions are, these inductive definitions are to prove this. So what we have is we have a finite simple graph which is a d-manifold, and we have a function which is locally injective. This means if two adjacent two adjacent vertices have not the same function value. It's a color. We can look at the level set. F is equal to C. It's a level set. So these are all simplices on which F minus C changes sign. This is a D minus 1 manifold or empty if C is not in F of B. So the only changes which can happen, topological changes which can happen, are on the if the function value takes a value on the vertex. So that's wonderful. So that's actually, this level set is even not defined if the C is always has to be assumed not to be in the vertex set. And it's kind of a magic, because when you look at in the continuum, where even very, very nice functions like x squared plus y squared minus c squared is equal to 0 can have singularities. So this is whole algebraic geometry is based on this kind of study. They're not manifolds in general, the level surfaces of polynomials even, but here it's always a manifold, always, if it is defined, or empty, can also be empty. Now, if you look at if you look at this kind of in 2 dimensions or so, kind of with a regular triangulation like this is something one has kind of looked at in statistical mechanics, for example. If you look at Ising model or so, and this notion is very natural. But I have not yet told you what the graph is. So what we have is these are just the simplices are vertices, and then we have this is a subgraph. This is a subgraph of the barycentric of G1, which is V1, E1 of the barycentric refinement. So the barycentric refinement, it's easy to see that the barycentric refinement is a D graph, also a D manifold also, which is also a D manifold. Actually, I can prove you that quickly, because the proof of this Sard theorem very much relies on hyperbolic structure. So what we have is a hyperbolic structure on the barycentric refinement with respect to the dimension functional. So if you have a simplex, then you have you have a stable and unstable sphere. The stable sphere is S minus. These are all simplices y, where y is contained in x. I mean, that's actually the definition of being connected. It has to be either subset of x, or it has to be a superset of x. So that's what we have is so y, and then x contains y. So this is S minus, and let's call this S minus and this S plus. And then what we have is S of x is always the sum, the join, S minus x plus S plus x. So the join of two graphs, if you have two graphs like this, two graphs, you take the disjoint union and you additionally connect everything with everything else, everything here with everything here. So that's the join. And it's easy to see that the join of two spheres, of 2D spheres, join of a K sphere and L sphere is a K plus L plus 1 sphere. A 0 sphere plus a 0 sphere is a 1 sphere. A 1 sphere plus a 0 sphere is a 2 sphere. Right? The octahedron, which I just disassembled here, the octahedron is an example of this is a join of C4 with the 0 sphere. So it's a join of a 1 sphere and a 0 sphere that gives us a 2 sphere. If I take this, I take a join again, I get the 3 sphere, and so on. So you get all the cross polytopes they exist in all dimensions. These are the only ones which survive in higher dimensions than as d-spheres. So in 2 dimensions, 2 spheres, there's only the octahedron and the icosahedron. The others are not. For example, the cube, as this is the hypercube, but if you look at the cube, that's not the sphere, because the unit sphere is not the sphere. One has to be very, very clear what the sphere is. So otherwise you get into this Lakatos problem. Lakatos was writing a whole book about that, about the problem of defining what the polytop is. And especially in higher dimensions, there was lots and lots of confusion. That's why most of the combinatorial topologies look at convex spheres which are given as convex sets in Euclidean space. But for us in the discrete, we don't want to look at Euclidean space at all. For us, Euclidean space doesn't exist. So that's all has to be defined purely combinatorially without going into any realization, Euclidean realization. So what we have is this beautiful hyperbolic structure, which is like a stable and unstable manifold, which together gives you the sphere. So the sphere is then the join. Here, the suspension, the join of the 2 spheres is again a sphere. So that's very nice for the homotopy manifolds, which are kind of more forgiving with requirements, so that they can be used in data analysis. If you take a random set of points in space which are dense enough and connect them, if they are in some neighborhood, you get a homotopy representation of the manifold, which is very, very nice because you don't have to worry about triangulation. This is very important for this is by definition, this is clear that this is a sphere because this is a boundary of a simplex. And in this case, also here you can quickly see that this is a sphere by just collapsing x together to a point, and then you get the simplicity complex, which is a sphere. So this is the proof that the barycentric refinement of a d-manifold is again a d-manifold. So it has all the same properties. But it has additionally more. It has also this hyperbolic structure. And now this level surface is also part of that barycentric refinement. And what we have is, you can quickly see why this actually is the proof works. So what we have is, when we look at S plus, because f changes value on x, it also changes value on y, because x is part of y. So all of this stable part is also part of that level surface. The only thing what happens is when you have this is a very simple object. So this is a kind of, for example, for a the sphere is the simplicity complex without the cell in the middle. So this is a C3. So C3 is different from K3. K3 is the complete graph where you also have where you have in the Whitney complex also the. So C3 is the simplicity complex, which is just the boundary complex, which is not the Whitney complex of a graph anymore, but it's a sphere. And when we take the level surface in this sphere, we always have the property that if you take a level surface of such a sphere, which is the boundary of a simplicity complex, that's again a sphere. It's just 1 dimension lower. And so you have the join of something 1 dimension lower with that. And so that proves that also in the level surface, every point has a d minus, in this case, then a d minus 2 sphere as a unit sphere. So that shows that this theorem, so that's a d minus 1 manifold. The level surface is always a d minus 1 manifold. It's an absolutely fantastic result because you don't have to worry about singularities. It's very, very nice. Singularities are going away. And so whenever it is defined, whenever you have a function really defined a random function you take on a vertex that is locally injective, probably with probability 1, and this random surface, this produces you a surface always, or something empty. So let me explain what the homotopy d-manifold is. So what we want is, we make the same definitions like these inductive definitions, but what we just want is that the unit spheres are homotopy d-1 spheres or contractible. And it's important that we allow contractibility also. So for example, this is an example of a homotopy. This is an example of a homotopy 1 sphere. So even though it's two-dimensional, typically these graphs have much larger maximal dimension. So in this case, there are vertices which are unit spheres which are contractible. There are K2 here. Or then there are unit spheres here, which if you look at this graph here, let me just make it simpler here. That's an example of a G. This is a homotopy. One sphere, one manifold. It's actually a homotopy one sphere. So the definition is like that. You can take away things as long as you don't really destroy another sphere which is not contractible. So that's important. We cannot take away this point here because, I mean, that's not a homotopy step here. But for example, if you look at this graph here, this wheel graph, this is a homotopy two manifold with boundary. So, I mean, for us, with the definition, this is actually a homotopy two manifold because what we have is it's already reduced. You cannot remove anything here. If you remove this vertex here, what you do is you make a homotopy step, but you actually destroy this sphere here. This sphere is destroyed. So you cannot do that anymore. So that's I was thinking about this for many weeks, because what you really want is you want to have the nature of space. You want to have the dimension, the nature of the when you look at data. If you will come to this. If you look at graphs which are defined by data, you take points in space randomly, like a point cloud given by a scanner, and you connect two if they are close enough to each other. This is a total mess in general, but it is a homotopy. It's a homotopy d-manifold if you are scanning a d-manifold, which is really nice. If you take this here, you can actually take this away. This you could take away, and it would still work. In this case, we can take this away here because we don't destroy any unit sphere. So we can take this away until we get to the sphere. So this is a homotopy one sphere. You can also see it like that. The unit sphere of this point is this K2 plus K2, this joint union of K2. That's a homotopy. That's a homotopy. Homotopy zero sphere. So this is equivalent to just 2 points. This is a zero sphere. Anyway, graph complements of linear graphs are always homotopy manifolds. They either have a boundary, balls, or they don't have a boundary, and they are spheres. Okay, so this is an opportunity to show a little bit also virtual graphs. So what we have is, first of all, homotopy, so d-manifolds with or without boundary. So I've given you examples, right? So this is an example, which is one homotopy, one sphere. You have this is a homotopy, two ball. By the way, if you take a complete graph Kn is a homotopy, zero ball. It's just homotopic to a point. You can remove that. We don't destroy any spheres when we do that. So that's kind of what happens. If you take something like that, a string of maybe complete graphs, if you take a string of complete graphs like that, this is homotopy one. And I give you examples then afterwards with data when you generate them with data. Let me just explain you one thing more here. If you look at this graph here, this is not a homotopy one sphere. Even so, it's homotopic to a one sphere, but it's not a homotopic one sphere because this sphere has a 3-point graph so this is kind of more like a variety because it has a singularity here. It has also a singularity here. We can take this singularity away, and that's already bad. We can take this singularity away. If I take this away, now we have a homotopy. This is a homotopy one sphere. And the reason why it's a homotopy one sphere is because we can take away this vertex we can take away because it doesn't change any unit sphere and it's a homotopy step. We can take away this one. We can take away this one, and we can take away this. Now we cannot take anything away anymore. So this is actually now one sphere. It's a cyclic graph. By the way, within the class of homotopy, you can move from one to the other by just making homotopy deformations. This is not possible here. We cannot make a homotopy step. If you have a sphere like this, this is actually what we have here is a real two sphere. This is a two sphere because every vertex has a cyclic graph as a unit sphere. So we cannot take anything away. If we take anything away, we make it collapsible. But within the class of homotopy spheres, we can do that. What we can do is we can make it thicker. So we can, for example, make it thicker like that, and then add more stuff, and then remove the inside thing. It's a little bit an exercise how to do that, and you can actually, within the class of homotopy spheres, you can get from any cyclic or any sphere to any other sphere. How do you do that? You cannot do a homotopy deformation directly here, which remains in spheres, but you can do it within the homotopy spheres. You can do that. So what we can do is we first add a new vertex. That's the first step. And then the next step is, these are all homotopy spheres. You can add another one. This is also a homotopy step, and it's still a homotopy sphere. And now you remove this one. This can be removed because the unit sphere is contractible. And so you get here. So we have to make this deformation. So C4 to C5 deformation within homotopy 1 spheres. So that's the power of it. You can do things, you can do deformations which you cannot do within the full rigid topological case, right? If you actually do here, this is no more a two sphere. It's no more a two sphere. It has a three-dimensional component. It has a tetrahedron part of it. So this maximal dimension is 3. Topologists would realize it in Euclidean space, and you would have a three-dimensional part of that. That's not. But it's a homotopy sphere, so that's kind of very, very, very nice. So January 2021, I looked at the graph complements of Cn are spheres, or so for example figure 8, that's a wedge sum of two spheres. And then the dual graph of Ln is R spheres or balls. And this all works very well because we can describe the unit spheres and intersections of unit spheres and everything. These are all of this type. So it's a very nice class of objects. But it gets arbitrary high, large dimensional spheres you can model like that. But they are homotopy spheres. So for example, if you take L3, so the dual graph, what is this? If this is G, so the dual graph or the graph complement of this consists of all vertices which are not there. So this is self-dual. Like C5 is self-dual. If you look at space and you make measurements, what you can do is you take points, you make measurements. You can only do finitely many measurements. You are a finite creature, you can have finite, our computers are finite, our scanners are finite, everything is finite amount of memory. You can do only finitely many, you can only measure finitely many points. But now if you take this thing and you make a scan, for example, you make a scan of this plane, and we want to kind of model this as a geometric space. We want to take into account, identify things which are close enough. So if we take kind of an epsilon or an h bigger 0, this is a threshold. Physicists would take, 1.6 times 10 to the minus 35 meters, like the Planck constant. In a scanner, you would maybe take one millimeter or whatever the accuracy of your scanner is, or whatever your accuracy of your measurement is. Maybe it's 10 to the minus 5, maybe it's 10 to the minus 10 if you are on this atomic level, maybe it's 10 to the minus 35 if you're on a really kind of fundamental level. But it doesn't matter what the age is. What happens is you take now a graph, and what you do is if 2 points have the distance smaller than that, you connect them. So what happens when you take this is a very, very high dimensional thing, and I actually generate you here a couple of graphs. I generate you a one-dimensional graph, and if that's a model for a one-dimensional graph, if you like that, it's a model for a floating point. Floating point arithmetic on a computer just stores finitely many numbers, can only deal with finitely many numbers, and Oscar Lanford was very interested in these kind of questions. What happens when you do it on a fundamental level? If you're kind of if you do some simulations, you do geometry on a computer, what is actually happening there in the very, very small? And it's very interesting, and it's actually homotopy one manifold. If you scan a two-dimensional space like that, it's a homotopy two manifold. Whenever the points which are too close that they cannot be distinguished, you connect them. You don't do measurements. What you get is a graph. No distances between the points, but you just get the graph and you illustrate it. I show you here a two-dimensional graph. A two-dimensional graph which is I just obtained it by throwing points in the plane randomly and connect to if they are close enough to each other, and then produce the graph. Graphics which produced the graph had no idea that it came from a two-dimensional thing, but it just saw that it was two-dimensional. And it's actually what happens is every unit sphere is, if it's kind of in a reasonable range, this has to be still investigated, but what happens, every unit sphere is either contractible, that for most points the case, or then it's a one sphere. In this case, for most points, you actually have the unit sphere is contractible, but it can happen so that you have a zero spheres. And now it can also be that everything is contractible, but then homotopy means that you can take away points. You take away points until you reveal spheres, and these spheres have to be one sphere, zero spheres. In this case, in 2 dimensions has to be one sphere. In 3 dimensions, I show you a graph. In 3 dimensions, this graph is obtained by looking at data, just random data, and you connect them to huge dimensional space. If you look at the maximal dimension. One of my heroes is Ed Nelson, a mathematical physicist, very original, has written lots of things on mathematical physics, like Brownian motion and stochastic processes. He was also interested in the foundations of mathematics, and he was building an extension of Zamenhof-Frenkel with the continuum hypothesis, which internal set theory, 3 axiom, internalization, standardization, and transfer. So these axioms tell you what it means to be non-standard. So there's a new word, a new property, non-standard, and this non-standard property is axiomatically defined, so precisely as precise as our mathematics is ZFC. It's a consistent extension of ZFC. And what you then say, then you have an H bigger 0 non-standard. So this is smaller than every C where C is standard. You can talk about infinitesimal notions like Euler did. And in some sense, it allows you to discretize space. You have a space, like torus, and there's a compact space. There's a finite set which is infinitesimally close to every. There's a finite set, so there's an n, a finite set, and then you can take an h bigger than 0, which is infinitesimal, and then you can find that n, and you can work with this n, and you get the simplicial you get the graph, you get the simplicial complex of your manifold. So this is what I would call then radically elementary geometry, because what you do is you just look at finite points. You look at the compact space as a finite set of. So I myself, since I learned that as a student, I think about this like I think about compact sets as finite sets, and it doesn't harm me. But you cannot prove things using this language usually because nobody knows about it. But where the whole calculus collapses down to a very small part, it's much simpler. If a manifold, this gives h bigger 0 gives you a graph. So I don't yet know what the exact conditions are, but what you just want, you want to have enough points here, d plus 1, not just, you want to have just enough points so that the space is really kind of, you know, covered well enough by the point cloud. You see that when you look at the scanner and you scan things and you don't scan it carefully, so you have holes, you have things which are not covered by the points, and so that you have to fill these holes. Why this is exciting is because if you have for example, this torus has a rotational symmetry, right? So this rotational symmetry, actually there's T2, this is actually a group, so this is T2, this is actually a Lie group, it's T2. It's not, so if you have a flat, if you have a flat metric, if you take a Clifford torus, or if you have a flat metric, so you have a very nice group action. And for a sphere, for example, if you have a round sphere, nice round sphere, this is actually a very nice round sphere here, completely smooth. So you have a SO3 invariance, so completely rotational invariance. So now what is nice is with this point cloud is actually invariant under all standard rotations. So if you take a standard rotation, whatever standard also, this is SO3 is compact, right? It's a compact Lie group. SO3 acting on S2, and you have also here, you have a finite set of rotations which you ever can consider. You know, we are finite creatures, we can only do finitely many rotations. And so all the standard rotations which you can define, so all the standard, there is a finite set of rotation which is infinitesimally close to any of the standard notations. So you have also a finite set of rotations, and you can make this invariant, just make the set a little bit larger so that it's invariant under the group action. And then what you have is a finite set which is invariant under every finite set which is invariant under every rotation which is standard. And so that kind of solves the problem of having a continuum symmetry. You have a continuum symmetry for everything what you ever consider, whatever you do with this rotation group, whatever you consider, you have still that symmetry. And I want to stop here.